Whoa. Magnifying glasses. Sorry. Magnifying glasses are awesome because, well, let's think about it first. If you have a nice green eye and there's a lens right here and you're looking at something that's very far away, then the height of the object corresponds to the height of an image right here on your retina. Rays come in, form an image right here. Because this angle here is equal to that angle there, the height of the image is similar to the height of the object and has something to do, well, here's the distance of the object. So the distance of the image is always going to be your eye. That's interesting. But if you move closer to a certain thing, or you pull that thing closer to you, like if I'm sitting around grading papers typically, and my son says to me, "Hey Papa, look at what I've got over here." I say, "Bring that over here, boy. I can't see a thing when you're that far away." And so he brings the thing closer, and it might be something like this. And that's cool because then I can see it. Let's say my near point is right here. There's my near point, and I label it with an N. That means that's as close as I can possibly be to something and still see it focused. And this camera has a near point also. We'll get to that in just a moment. But if I'm just at my near point, then the image that forms in my retina will be quite a bit bigger. The height of the image is much larger because theta prime is the same here as theta prime. So the beautiful thing about getting closer to stuff is that you can see it with more detail because these sensors here are only so big on your retina. They're actually fantastically small, and you can see things with great precision. You're like, I don't know, better than this stupid camera that I'm using right here. Your eye is an amazing instrument, but will you agree with me that you can see things in more detail when the image is taking up more space on your retina than when the image is taking up less space on your retina? That's why you like to get closer to things to see them well. Now, the issue with the near point is the closer you get to a thing, the bigger it is on your retina, but at some point you can no longer strain these cilia muscles to get that lens to be bulby, 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 like maybe you go here from a lens that looks like that to here that a lens that looks like that. You are deliberately squishing that sucker down and making it incredibly convex so that we have a much tighter convergence because these rays here are diverging more than these rays coming to your eye here. Because, well, again, when you are near to something, its rays are dramatically diverging. When you are far from something, its rays are not diverging as much, and when you're infinitely far from something, the rays coming from it are parallel. So when you look off into the distance, considering perhaps your next move in the game of life, you are looking at something that has rays that are not really diverging. Here's the thing, though. I want to bring the object closer. And in order to do that, to bring it closer than my near point, well, let's do a little bit of math first. First, I want to tell you that the height of the image, well, here's what I want to define. I want to define this angle theta. And if the angle is reasonably small, and for most stuff that you're looking at, it's not like 90 degrees. It doesn't fill everything that you're seeing, right? If I'm looking at this theta, I'm about, what, half a meter away from it, and it's only about, 2 centimeters tall, then if I'm looking at this theta, I'm thinking that the angle is really fantastically small, and I can see the theta pretty well. It's a nasty looking theta, but I can see it. So I'd like to assume that theta is approximately equal to tangent, sorry, this is supposed to be an approximate sign. Theta is about the same as tangent of theta. And let me see if I can argue why that might be true. Tangent of theta, well, tangent of theta, here's why I want it to be true. Because the tangent of theta is then the opposite side divided by the adjacent side. So we can do some cool math there. That's fine. But the reason it is approximately 2 is tangent of theta is exactly equal to the sine of theta divided by the cosine of theta. And of course, you know that the sine of theta is exactly equal to theta minus theta to the 3rd divided by 3 factorial plus theta to the 5th divided by 5 factorial minus theta to the 7th divided by 7 factorial and so on forever. And cosine, oh, if you don't know that, you should study your Taylor series because they are a beautiful thing. 1 minus theta square over 2 factorial plus theta to the 4th over 4 factorial. Oh, look, cosine gets the evens. Minus theta to the 6th divided by 6 factorial. That's where they are. And then plus, and that goes on forever also. But these terms are progressively smaller and smaller, especially for angles that are less than 1 radian, because I've got the numerator getting really small as I'm squaring and, well, multiplying higher and higher powers of a very small number, and I'm dividing by this enormously increasing denominator. Do you have any idea what 70 factorial is? It won't fit on my calculator. My calculator thinks for a little bit and it's like, shut up, I can't do that. And these also are getting fantastically small as each progressive term gets further down this series, an infinite series nonetheless. Each of the terms gets smaller and smaller. So let's say we drop this one and we drop this one right up in here. And I'm going to take those two equations then. This one says sine theta is about theta, and this one says cosine of theta is about 1, and I'm going to plug them in here. So this is approximately the same as theta divided by 1. And that's cool because that's theta. That's why tangent of theta is about theta. Here's another reason. Get you a graph of theta and tangent of theta versus it. Here we go. I'm thinking it's going to do something like that. What beautiful thing about it is right at the origin, right around theta is 0, I mean for every small angle, gray maybe, gray. Look at that. Slope of it is 1. It is in fact there that tangent theta is just about the same thing as theta. If you start diverging from that line like there and there, well, I guess it's no longer true here. There's some difference between them. Those are these terms creeping up in significance because the powers of theta and theta gets bigger, so we get a more of a distinction between tangent of theta and theta. But perhaps I digress. My point is, I can say that theta is about the same thing as the height of the object divided by the distance of the object. And the frustrating thing is, here's the frustrating thing. The closer you get, the harder it is to focus, until ultimately you can focus no longer. So the beauty of a magnifying glass is this. You notice that, well, did I tell you that I collect coins? And this is not that fancy of a coin. It's from 1951, and it's a US quarter. But the cool thing is somebody paid me a quarter for something, and they dropped this off on my desk, and it's made of pure silver. Yes, awesome. Every quarter before 1964 is, including 64? I think including 64. Anyway, I'm going to bring this up here, this pure silver quarter. It's worth like $4 or something. And I'm going to bring it up here, and I'm going to point out to you that we can no longer focus when it's this close, right? See that? But I've got a lens. See that lens right there? And I'm going to set that lens on top of the quarter as we get up here, and I'm going to say, well, can't focus, right? We're really close. Ooh, the quarter is subtending a large angle on the sensor inside this camera. And I'm going to put this in right here, and I'm going to point out to you that, whoa, we can now focus. Because what I've done is I've formed an image of the quarter that's infinitely far away. The image is infinitely far away, and I can use it as a magnifying glass now because even though the quarter, here's the quarter without the magnifying glass, even the quarter is fantastically close and the camera is trying to get it to focus, it can't because it's so dang close. With that magnifying glass, the image is infinitely far away, so the camera's like, oh shoot, it's easy to focus infinitely far away, and your eye feels the same way. Look at that. Isn't that beautiful? Now, let's draw ourselves a little bit of picture of that sort of thing. Ooh, it sounded like silver too. That's fun. Okay, so here's my point. If you have an object a certain distance away from your eye, here's your eye, and we're at your near point. This is the best option that you can do without a magnifying glass. If the object is at your near point, then this distance is n. And the height of the object is right there. You want to be able to do this situation right here, where you're looking at the object and it's inside of your near point. So here is still your near point, but you want the object to be something like right here. And you would certainly agree that if we do the angle, we look at the angle right here, and therefore the angle that will be subtended inside of your retina as well. This angle here we'll call theta. And this angle here we'll call theta prime. As we're coming in through here, and you see that the image inside your eye is much bigger, You want to be able to put the object inside your near point, but the only way we can do that, this is going to be theta prime, and that's theta right there, is to have a lens in here that causes the rays not to so dramatically convert or diverge, because they're diverging too quickly for you to be able to get them into an image. So we need something up here that's going to cause them to converge down a little bit, and the way to do that is with the color orange, I think. We put a lens right outside of our eyes and say, no, you're going to have to bend in a little bit more, so these rays that were diverging really dramatically are brought in a little bit. In fact, oftentimes they're brought in exactly parallel, and then as they reach your lens causes them to form an image right on your retina. That's awesome. Your lens and the outside lens, this is the magnifying glass. So the cool thing is, I can get it ideal if I bring the object to the focal point. So I'm going to say this distance right here is the F. It's the distance between the lens and the object itself. And that's where I get maximum magnification, because now the image that's formed, look at this ray right here. This ray that's approaching your eye and this ray that's approaching your eye from the object, those lead back parallel, in fact. They both seem to have come from infinity. So the image that's formed of this object by this lens is infinitely far away, but it subtends an angle theta prime when it comes into your eye, which is bigger than theta. So let's do a little bit of math right here. We've got, well, this is the height of the object in both times. And remember, we were arguing that theta is approximately the same as the height of the object over n here. And theta over here is approximately the same. Look at this triangle. It's the height of the object over f instead. Height of the object over f. And I could argue for you that magnification, the magnification of this lens, is brought to you by the fact that we've got the object image subtending a larger part of your retina. That's why things look bigger. And I'm going to say that magnification can be defined as theta prime divided by theta. This is, whoa, magnification is not always 1. So I'm going to say magnification is defined as theta prime divided by theta. So this is the new image size, that's the old image size on your retina, and it's much nicer and bigger and happier because of that. Now, let's plug in these theta primes and thetas. I've got h, wow, dang it, this is supposed to be theta prime. Theta prime here, theta here, okay, good. So I'm going to say h naught over f divided by h naught over the near point. And so the magnification of a lens, if it's used properly, there's a magnifying of a magnifying glass, is just n over f. And since your near point is bigger than the focal length of the lens, you can get significant magnification using these suckers. So question for you, which one of these will be better? Which one of these will be better at magnifying? You tell me. All right, goodbye.